We're going to continue with the Davis-Putnam algorithm. Now, I did some thinking about it. I haven't touched this, but uh, basically what I've done is turns out not to be correct. Because if length of clauses is 0, it's actually sat. So we should actually immediately say that's sat. Now, what we're actually looking for to decide if something is unsat is an empty clause. Unfortunately, I feel like we need a good amount of examples to kind of look into this. So actually, we were finding that this problem was sat, and actually it was working. So first I thought the tautology might be wrong, but actually this makes sense. So there's nothing wrong with that. But where we have a problem is an empty clause. Now, somewhere I looked into this. You see this, if length C equals 0. But basically, we do not want to do this. So if length C equals 0, actually we have an unsat. So this is actually the criterion. So we could say else if any length C for C in clauses equals 0, if there's any empty clause, of course it can't be satisfied, so you can just return that it's unsat. So something we need is more examples. Now I'm looking kind of around for, because the problem is, since we're using such an inefficient algorithm with the for large instances because of the exponential clause growth, actually all the instances I have are sat, and I was hoping we could get some information on whether we're going to have uh, an actual formula when we get the sat back. Now, there are ways of adapting the Davis-Putnam algorithm, and that's probably what we have to do. We probably have to go in and adapt. And as I said, there's probably some bugs that I think are in here where we're, doing something that we shouldn't do in here. But again, the problem is it's not really testing the code because it's getting onto the case splitting. Yeah, so let's maybe look into this. Maybe we can always write some simple examples, possibly. But the problem is the examples are so simple that I am not always happy with them. But I mean, we can write like a 2-sat example. We can use this one I found on a web page somewhere where they're looking at a simple example from die match format. But again, we don't need to take the die match. We can just, start doing something different here. So there's a test formula. Test F2 is going to be this one. 1, 2, -3. I just found a web page with this. Probably need to look for more web pages. There would be 2, 3, and then -2, and -1, 3. And we can just kind of see what happens here. Uh-oh, stop iteration. Yeah, so actually the order of doing these operations is really, really critical, and you have to be really careful. So this case will not hit here. It'll obviously, the tautology case, it'd be like if there was Q and not Q alone in a clause type of situation. So then we should actually check here, because that'll happen from the unit propagation, and that's why I'm saying it's one of those, uh-oh. Print the clauses map and see what's going on here. Oh, I guess actually both checks need to be here. Come to think of it. Okay. Something weird going on here. Um, well, the first one sat, so uh, again, we're not really printing because I want to print solutions, and so I'm not really. I don't really have something set for the Boolean mode, and plus we need to check that it actually works. And I'm not totally sure that all this code is even being tested yet. Okay. Well, it's crashing here. Oh, because this is needs a comma here. That's Python stuff. Okay. Oh, you see here. Here's what the type of errors. This is what I want actually. I want this type of thing to be occurring because yeah. Okay. I see -2. Yeah, so it's actually, this is what we're hoping can start occurring is that we can start getting parts of solutions, but where the solution caused all these tautologies to just resolve, I'm not exactly sure how we can just find the solution without. I think what we'll do is we're going to kind of uh, take ones that we've found are part of an actual solution, because actually the Davis-Putnam method, as far as I can see, it's only going to reveal clauses in here which are guaranteed in all solutions. So when we're collecting these solved vars, these are like universal, they must be true regardless. And then we're going to have what I'm calling the free variables, and those could have different combinations, and we don't know how many. But what we can do is we can then go through a different version of Davis-Putnam, and we can figure out what they are. And then we can actually say that we've pretty much solved this. Although there's a lot of complexity issues here because we're using remove, and we're going to fix that actually. We're not going to just slough this off. We're going to do the right job here. So where is this happening? Line 44 in unit prop. Okay. Oh, because we're going to delete this map. So yeah, we don't want this. So if just ignore the case maybe. Aha, yeah, tuple has no attribute remove. This one, as I've said, there's a bunch of these kind of efficiency things. So there's two levels to this. Right now, my instinct is to just use a set of sets, but I don't think Python will allow that. So we'll just maybe use a dictionary keys, like a fake dictionary, just to allow that. Because we could use frozen sets, but it would be just as, although in a certain sense we could just, I mean, there's different ways we can figure this out. This is the only place that we're deleting from a clause. One option, well, actually it's not an option. You see, the problem is we have references in map here, so we'd have to update all the references, delete the old tuple, put in the new tuple, but tuples are immutable. Changing it to a list would be, ridiculous. So the first instinct that I have here is to fix everything right off the bat. So clauses right now is a list. We know that removing from a list, if that's what we need to do, is not going to be efficient. So we would rather have this be some kind of a dictionary We actually want to just use pointers or references, and it's Python, so we're going to have to come up with some approximate equivalent. Now, one idea is just to take the clauses and to change their format right off the bat. So right now we have a list of tuples, and the easiest thing to do here is to do something like this. Okay, it's a set. We know that these have to be mutable. And as I said, I don't think this will work, but we'll just make it into a dictionary, and I think that will work. So we'll just say C or C. Oh, that doesn't work. So actually, the easiest thing to do would just be to say set, because it'll change it from a tuple. I mean, we could use star C with the brackets, but I don't think that's as efficient. So, in fact, I'm going to try not to use that anywhere. I guess I used it. Oh, well, actually, no, I didn't, because there's duplicates. And another thing is this will remove duplicates, and that's another rule we could add, but we don't need to add the rule if we're using a hash table like this. We can actually uh, enjoy the fact that, well, the set will take care of that automatically for us. That's actually a useful optimization. So, yeah, okay, I have a student messaging me. Let's see. Okay, so what I can do here is, let's see. Again, it's kind of a big rewrite here, but it doesn't matter. So this is constructing a set of sets, which, as I said, it's going to complain that it needs to be hashable, and a set isn't hashable because it can change its value. Now, I'd rather have it just use references, because we're going to be referencing these, and actually that kind of clever trick with using referencing and pointing in Python is actually saving a lot of potential problems. So let's see if we can do this with a set of sets, but we'll just adapt it to a dictionary. There should be a way we can, I forgot the notation to make a dictionary comprehension in Python, but we should be able to do that very straightforwardly. And then we have a great solution in the works here. So I'm just going to start retesting stuff randomly. So yeah, unhashable type set. Now this is exactly what I said was going to happen. Now, how do we make a dictionary comprehension in Python? I forget how to do it. I just need to see it, one simple example to remember the syntax. Uh, okay, wow, that's not very helpful. Finding lots of useless examples for how to do this. Oh, I guess we just do what I thought it was going to be. So we can just do this, for example. I guess that'll work. Oh, unhashable type. I thought there was a way to do this. Maybe this is going to be an issue. I know I could use a frozen set, but it defeats the whole referencing trick that I want to use. Again, I want just like a reference, something that will allow me to add and remove references very efficiently. I'm reading a lot that says that lists cannot be a dictionary key in Python, but well, Yeah. Obviously, we can use frozen sets, but it won't work if we're changing items. Hmm. Other idea is just to delete yeah, I mean, that might, but then we have to go do some extra work. I don't know. I mean, that would definitely work though. So, hmm. Set of sets. I thought there was a way to do this. I don't know why. So I want a dictionary where the keys are reference to an object. Yeah, okay, this is. I should search for what I want here. Obviously, that would be really efficient. And let's see if there is any way of doing it. Hmm. I mean, the key is that their hash and equality must be overridden on some kind of option. Okay, well, I don't see a good way to do this. Hmm. Yeah, I don't see a good way. So I guess just re-add the item and keep this straightforward. I don't see a way of doing it. I mean, there are some other solutions to this problem, like making a class, but I don't want to go to that level. Should be an easier way to do this. Hmm. Well, if there's not, then the thing that's annoying me here is I know there's some tricky way to do this. There's got to be a tricky way. Okay, well, I'm looking on the web and I don't see anybody mentioning a tricky solutions. Because the problem with referencing an object in Python is, I mean, technically a mutable object could change its memory address and this, that, and the other, and that's probably why they don't offer that. Okay, well, easy enough. Um, We'll use frozen sets. And we'll actually just use a set, not a dictionary then. So that's actually a pretty good improvement. Okay. So where do we crash first? Case splitting. So now we can't append a clause. And actually, this should be a frozen set. And we should just add it to our set. All right, that looks ugly, but you need an iterable, and so we have to use an extra. Well, it doesn't matter. Again, frozen set is not subscriptable. I agree with that. But since the length is 1, we can just say, actually, this looks nicer anyways. Next iterate. And there's going to be more of these coming. We don't have to worry. We're expecting it. There's no remove on a frozen set. That's right, there isn't. So what we can do now is we can actually say C minus. Yeah. Okay, this constructs an extra set on the way. I don't exactly like that, but it's okay. So new C equals this. Now this is where we run into some kind of problem with having to re-reference everything. But we don't have to re-reference anything in minus X map because we're deleting it anyways. So we'd say clauses dot remove C, clauses dot add new C, the new clause, and then we need to go through for y in C, if y equals minus X, continue. And it's going to be the same tedious thing here. Maps of y dot remove C, maps of y dot add new C. Wow, that definitely changed things. Okay. Oh, it's ugly. That's what I can say about that. Okay, now we've got like a starting point here. Maybe I'm printing more than I need to print here. Lots of debugging going on in here. Doesn't look right. Okay, this this definitely looks wrong because if it shouldn't have these as clauses. Yeah, that's not right. What was going on? How did that happen? So I see we have 3 minus 3 minus 2. 2, 3 minus 3. I see we have this going on. And it looks like one of these is screwing it all up here. And there's definitely not any unit clauses at that point. So tautology must be screwing it up. Yeah, I think. Well, these clauses should be removed. They are tautologies, so. This is right. This is an empty list, but then I see it printing this. Oh, they're all empty, yeah. So then why didn't it delete them? Oh, I think. Deleted minus X. Okay, I see. This is an empty set right here. Uh-huh. And then it's like adding them back. Okay. So the problem is thinking about like when, again, case splitting, yeah, it deletes from the map. But the tautology case also has to delete from the map as well. So what's happening is it's got the tautologies here, and after you process tautologies, potentially you're left with empty map elements. So basically, we could just say if length of map m and the length of map minus m are both 0, then to avoid the pure literal situation from being a screw up, we can just delete map m, delete maps minus m. And a tautology is like a kind of unknown variable at that point. Like it's one that won't end up being resolved. Okay. Yeah, I still see this. I see this. I'm not sure I like what I'm seeing here. Uh, kind of confusing output right now. But anyways, yeah, it seems like this was fine, but then it kind of got into this loop and it got the same issue going again. But there aren't any pure literals, are there? No, there definitely aren't. I guess this can happen anywhere. I guess we have to like. Okay, I'm not happy about this right now, but just to make it work, the problem is we could be removing from all over the place. But as far as I know, only this tautology would lead to this, as long as we've done our reductions correctly. And that actually is much better. This is what I like to see. So this actually is sat, and we get a result that looks sat. So actually that's good news. This one, okay, one thing I want to see is the solved variables. Now with unsat, I don't really want to see them that much, but I do want to see them here. -2, 3, 1. I think that is the solution to the equation. Again, that one kind of got forced though, so yeah, it is the solution. Okay, so that's not too bad. And other things we could do are like 1, 2, 1, -2, -1, 2, -1, -2. We can just do simple, trivial, this one basically. We can do 2-sat formulas as well. There's nothing wrong with doing that, just to see what happens. Aha, look at that. We got a problem. Key error. Okay, in unit prop on line 43, we got a key error. That key error is caused by... One moment. Think about that. I need more coffee. Coffee is code. Little bathroom break, coffee break. Yep. That's the word right now. Okay, so where we're at is that this situation's occurring, and somehow clause is not in clauses. This is really weird. Oh, because it was already removed? Yeah, that's true. Yeah, I don't like this kind of stuff going on here. This really feels... I do understand that we could have ended up adding a different clause. The only case this would happen in, though, is it's a unit clause and its opposite unit clause is there. So if that occurs... I almost want to treat these things as a special case so we don't run into this. But I think this... guess I have to just check it. Do we need that one? Here. Oh. Yeah, it's, I see. So it's only going to be this one case. Now this is like an extra aspect of this. I mean, do we even need this is kind of the big question. And this, yeah, okay, I guess we don't need that. So what I want to see here is just, with this one, I mean, we could print the solved vars, because actually I guess there could be some forced, of course there could be some forced solutions even in an unsat instance, like these logically had to be true, even though the rest of it can't be solved. Because of course, like if there's a literal that's never has its negation in there, of course these things are just truths. So we can look at clauses and we can like print out a little unsat. For now, this is like temporary stuff going on in here. Okay, so there's sat -2, 3, 1. Okay, so unsat, -1 and 1 both had to be true. Yeah, I guess it's giving us information like that as well. It's a special case that we might want to just look for. When we're doing the tautology, I kind of think, but that can only occur at the beginning or after a case splitting, whereas this could occur anytime during the unit propagation. We could get this kind of scenario happening. And you see, because we've already added the solved var. But the truth is, actually, if we don't want solved vars to contain anything that has this scenario where there's a clause with only one. One thing we could do is we could check for it over here. So we could check if there's an empty clause that comes. And if there's an empty clause, then we don't even bother appending this to begin with. It just starts to make it a little bit kind of cleaner. This sat case, now, I mean, we can always go back to our original just random instances just to see if there's more bugs and it's going to crash or what happens. Or it's ridiculously slow. Kind of to be expected. But I understand it could be ridiculously slow, but I feel it should be a little more optimized right now. I mean, there's different ways of writing this formula. Yeah, I guess just going through 200,000. Yeah, I guess the exponential explosion here is just really, really bad. The other question is, should we try to start enumerating solutions? Because that's what we're supposed to do here. We're not supposed to return. This is unsat, and we are returning unsat. But the question is, can we do something a little better here? So now, actually, I'm reasonably convinced most of this code looks, you know, semi-okay. I don't like this, though, because, again, this isn't like so many variables that we shouldn't be able to solve it. So we can see what's happening here. We can see the clause explosion, but the variable count is going down. And I just don't know how long until we get down to the next one, 28. It's like because each one's two a positive, negative variant of a literal. This is too slow. I can't imagine this would be this slow. But I guess there's so many clauses now. Mm-hmm. We've just got these big clauses coming into play here, and I suppose this is gonna kill the algorithm. Maybe we should just immediately start on DPLL. All right. Hmm. I'm looking at DPLL because I think we just want to move to that. Again, this probably is going to create so many clauses that it's never happening. Mm-hmm. Yeah, it's stuck in case splitting, adding like millions of clauses probably. Yeah, because there's just too many now for each variable, whatever variable it chooses, and so it's getting this big exponential type blow up. Wow. So I mean, yeah. Just to get an idea though of what's going on, like if there's some wow. This could actually no, this can't contain duplicates because these are frozen sets, and so yeah, these are all going to be somehow unique. There's no subset rule, but obviously if one of these was a subset of another one, and actually this would make you want to use like some kind of a tree to store them in because this is kind of ridiculous. So I can kind of see why it's so slow. Hmm. But I kind of want to move to DPLL for the time being and move back to this when we get a little bit more kind of practical wisdom on how to, actually get a formula out and some other things. All right, let's see. There's, another problem that makes this more complicated than I want it to be is that there just turns out to be several variations on which rules you can use to do this, and they're still all kind of coming under the same category of DP or DPLL. And, some are more optimized towards deciding SAT or unsat, and some are more optimized towards finding a solution, which I kind of want to do both, though. It gives you the deepest understanding. So the way it wants to do things is that we have to first off copy our formula in DPLL. So, and there's a way of doing this with DP too. I mean, this is, but then it seems vaguely. Well, let's do it. Let's do DPLL because it's where we want to move anyways. So here we can. Yeah. So. Well, we could do this recursively. Okay. Maybe we should do this recursively. We'll see. And we can just change it. We'll just call it DPLLR. So I've got DPLLR defined here. And what I'm going to do is I'm going to take this now and I'm going to use that to pass clauses in map. And then we'll just apply the rules recursively for now. We'll probably change it to a stack. Again, I don't think this will have so many thousands of nodes that it'll cause the Python call stack to become unusable for this task, but still. If we don't like recursion, we can get rid of it using a stack. So first off, we need to check if it's a consistent set of literals. It's this code. I mean, basically, there's going to be very much not any major differences between these. Well, at least it seems to me the biggest difference is going to be the amount of memory used. The amount of memory, yes, it's going to have to keep duplicating all the clauses and maps, but it should be much better in terms of memory usage. So at first we can just do DPLLR clauses map. We can just pass it and that'll be sufficient. We may need to return this. Again, if this is going to yield solutions or something, that'll be fine. At this point, we may also want to keep track of the solved variables. In fact, I definitely would like to do that. Okay, so now here we can actually just use the generator style to actually like yield solved vars or something like this. Again, we'll want to sort it or something, but big deal. Now, okay, so we've done the first two rules of DPLL. You can go look on Wikipedia, and this algorithm, just put a comment about it. So it's just right here. So first you check SAT. Consistent set of literals means for us there's no more clauses. The next one, if there's any empty clause, that means it's unsatisfiable because, nothing in a clause is the same as like saying false and something. So it's like a false clause. And so we don't want that. If there are no clauses, it's saying everything is true. And then we need to do the unit prop. Well, we have the code for that. I think we'll need to do this, yeah. And then we need to do the pure literal stuff. So uh, actually, we can do that first, I guess. I'm not sure if this matters too much. So you can see the code is looking extremely similar so far. While true, if the length of s equals 0, break. Okay, so basically we've got the same thing. But now, this is like the little crucial part though. We are also going to take a random variable. So we're going to use next of iter of, I guess I use map, right? Okay, so we have the same thing, but instead of calling case splitting, we're not going to do case splitting anymore. That's the key thing. And since we don't do case splitting, we don't need to do the tautology either, except maybe we should do it like up front. Because at some point you need to make sure there are no tautologies. They won't ever creep in later, like these, always true clauses with X and not X, but they could be there at the start. We want to kind of just make sure we've solved everything. So now you could actually just say X equals this, and then you can just call DPLLR, and we can just add to the clauses. However, this is a very expensive operation because whatever literally we are going to choose, it doesn't matter, but we're going to, first off, we have to add a clause. But we obviously have to have a different map, and I don't know the efficient way of doing this without copying everything. So, I mean, one thing we can do is just copy our map. We can use like even a dictionary comprehension to do that, and we can. Oh no, we can't. We can't. We have to copy the clauses first. Oh, it's just nasty. So, because the problem is the map has to have the right references. We're doing everything like that. So, I guess we just copy the clauses, and since it's a set of frozen sets, we can just say, and we could do it like this. P in clauses. So we just copy everything. And we'll call this positive clauses. So these are the positive clauses. Is there a better way to copy? Maybe we could just like use the constructor. I assume that's probably just as good. We can do the same thing for the negative clauses, but we can do that after actually, because in case it finds a solution. Now, if we want all the solutions, I think we have to search forever. Yeah, we have to search until it gets down to the base case. So if we could return like true or false or something, but this, so if we're gonna do it like that, we just do yield from. Oh, now I have to think about that. Yeah, actually, I guess we should do it like this. But if we use yield from, we have to return a list. Okay, we'll think about what to do with this. The problem with that is if it's unsat, we actually want to short circuit. But there's ways we can always look at the somehow. Ooh. Yeah, that's actually this could be. I have to think about how to get the generators right so we can actually kind of like spit out solutions and Of course, we want to see this work 100% and spit out the same solutions that the naive or other SAT solvers would spit out. So you can just say get SAT map of pos C, and we can just say solved vars. Oh, this needs to be a copy as well, doesn't it? Yeah, I'm not exactly happy with this right now, but we'll see about this. I feel like... So this is a generator. Yeah, it's a generator, and it's doing a list. And the only thing is, though, how can we tell it, like... Well, we haven't actually finished this yet because we have to add a clause to this. And that's going to be our new literal. So it's just like a simple frozen set. So we add x. And for neg C, we do a very much similar thing. So now we've got entire copy, and we make a new map for that copy. And then we go in with a copy of the solved variables as well, because there could be multiple solutions. So yeah, and so it's going to just keep guessing. Now the amount of memory it'll take will basically be the number of variables and times the number of the size of this map and clauses, which actually is decreasing in size. So I don't think it's a memory issue at all. So again, if this works worse than the naive way, that would be so weird. So we changed this to DPLL for now. Oh. Oh, that hurts. Okay, so something's not working like we want it to here. Oh, we're doing difficult instances already, okay. Okay, so it's getting stuck in unit propagate, but we don't have these huge clauses here. And that's the one thing, is we can apply the splitting rule also for DPLL, but then we get these huge clauses, and nobody wants huge clauses. It's just, yeah, can be a problem. Try some test cases and know why it doesn't work. Okay. Trying the first instance here. So it must have applied 1. Or -1, I guess here, -1. No, it applied 1, because then it gets rid of the -1 here. And here it gets these two clauses. And then it has -3 here, though. I don't know where that is coming from. If this is true, that whole clause is true. This is true, the whole clause is true. So it adds 1. Yeah, I see this. Which is weird because actually we're doing it very similar, but now it looks like there might not be a literal to choose anymore. Isn't that interesting? All right, so it's an empty set, yeah. But it adds 1, and it shouldn't get an empty set. 1 is a solution. So why isn't it working for this one, which is definitely a solution? Oh, actually, this looks right. This looks right. This looks wrong. Oh, it must be calling the next version. Yeah, -3. It must have chosen -3. Uh-huh. Okay, so if this is empty, then we should just probably... All right, so this isn't working. So it's going through all the clauses for -3, which includes that unit literal clause, and it should be just kicking it right out of the clauses. Ah. Wait a second. I think I know. That looks like a nice bug that I don't want to have. Okay, that's better. Okay, new C. Somewhere I have that in here. Oh, yeah, we don't do the conversion that I said we need to do. Okay. This is a problem too. All right, finally, some traction. Finally. Okay, let's do something about that. Okay, if this works, it would be great. I mean, again, we only need these unit prop and pure literal. And think we could do DP like this as well. We don't need the case splitting, and the tautology only needs to be done once at the beginning. So the question is, can we get case splitting to work? And again, it breaks the idea of getting a solution. Then it just gives us sat or unsat. And if we want a solution, we'll have to like go still doing a searching process. We'll still have to like go true and false and start trying to find solutions. But we might have a set of solved variables already, and we can kind of maybe do something with that. And when we find a solution, we can ban a solution, so it's easy to find more solutions. That's not a problem. Of course, it's inefficient, especially if it's so slow. Uh, but nonetheless, okay. So this is kind of like working. Um, the problem I see is that if it's unsat, uh, we would like it to short circuit as well. So if it's unsat, we want it to like do something maybe a little different here. Anyways, I want to see if it finds multiple solutions and etc. and so on here. Let's just drop this down here. I'm just gonna like use all the 2sat formulas too. Well, at least a few simple ones, because we want to just start knowing that this actually is working. Because if it is, that's good. If it is, we have like a basic, about as simple, I think, as you can make a reasonably fast or efficient solver here. All right, do we have multiple side do I? Oh. Still getting stuck. Still getting stuck. Never wants to be easy. Trying to like just think my way out of this one, but I guess we can kind of try to see what happened here. Wow. -4 is a solution. It's still got a clause there, but it's not in the map. How on earth could that happen? I'm looking at case splitting. That's irrelevant. I need to be looking here. Yeah. So if we're going to delete it from X, we've already deleted every clause. It's going to happen so fast, I don't think I'll be able to catch anything here. Catch it this way. Okay, so here's what's happening. Actually, that's kind of useful. Pulls out 3, but minus 4 is still here. That's when I see it pulling out minus 4 and minus 1. But how come minus 4 could still be here? Oh, shoot. I mean, it should never have a clause with a literal that's not in the map. The minute that happens, everything's broken. So this, yeah, this minus 4, somehow we're getting this weird situation here. Yeah, pipe more turned out to be a useful trick. It doesn't make sense because minus 5, staring at this, it seems to make no sense at least. Minus 4, minus 1. I mean, I guess it's coming from pure literal. Oh yeah, okay, that's what I'm missing here. Oh, because 4 is an empty set, so minus 4 becomes a pure literal, so it adds minus 4, a clause specifically with minus 4. This is tricky to... it's trickier than I thought this was going to be. Oh, I never add this to the map. Oh, this is terrible. Oh, that's like, yeah, these types of things are just not what we want to have. These types of bugs are worth a lot of pain in debugging. No surprise. Oh. In tautology? Seriously. Wait. What is even printing here? Oh, nothing. Okay, that's good. I guess. Oh, this is not very good. So we should initialize it even if it's, yeah, okay. Okay, I mean, that's not working, but it's sure better than what it was doing before. Okay, I feel like we're starting to get close to this finally working here. I kind of want to like look a little more at what's going on here. Yeah, this actually seems wrong to me. If I look at it, this doesn't belong here. You know there's at least a clause. Um, you know that none of them would be zero if you already had checked this. A question if we need to check it up front. I think we do, but for the time being, it almost seems better to just do it here where we can just try that. Oh. Oh, but this doesn't make sense. Doesn't make sense because this should print before it gets here. I don't. Oh, I see. It's like it is printing. It's just cut off or something. That's weird. I mean, that actually, apparently this is something different going on here. Yeah, I'm worried this actually has, the sat on sat case needs to come like before we go recursive even. We just need to like, prevent these little edge cases that definitely can happen. Um, this returning an empty tuple, and then we're yielding from that. Hmm. Okay, that looks a lot better. That looks a lot better. Now, one thing we have is that when it finds a solution, it will keep finding duplicates. And, ooh, well, some of these just look. This looks right, though. Sat. Looks right. I think these as valid solutions. Again, it's not printing all the solutions by any means here. Some problems are still here, but we're getting there. Unsat, we can see it prints 2, but it has -1 and 1 in there, so obviously, as I said, it's kind of meaningless what that would be in the context. Okay, so we don't want to yield from here, we want to return, I think. Should, no, still not working, because this would yield from, and this returns a list. But it also could return another generator list. Hmm. Honestly, though, this is looking a bit better. I know. I don't know why I'm getting stuck on this really silly stuff right here, where obviously the generator stuff in Python needs to be properly thought out. Mm. Oh, the negative ones we don't add. -x. My gosh. Make all sorts of little mistakes here. Okay. I would say it's okay, but it's only picked up 2 solutions here. 6, 7, -8, -3, -1. It's definitely picking up something now. I mean, but there should be 3 solutions to that one. And it's just a simple 2-sat problem. So, and it's interesting, it's picking up unsat on some of these as well. Um, yeah, and this yield from is not working. We could clean this up while we're at it. Easy thing. is in a sat case. Instead of solved vars, we could turn this. Okay, now they're at least in. What? Oh, yeah, they would be if this was working at all. It's from the list. I have to think about this recursive yield from. Okay. No, that still doesn't make sense. Oh, because I'm returning? Oh, yeah. Let's just yield this. Back to this issue again. I don't can't win with this. All right, we look up yield from Python. Must be not thinking about the yield from right. Okay, this does seem like that's the issue, but Okay. Whew. Okay. Oh, I think it's starting to work. Okay. I'm wondering what level I was gonna have to go here to get it to work. Okay. Yeah, we need to return after the yield. Okay, that's fine. So I see it thinks these are sat, 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 and then I see it comes back here. Okay, so yeah, we don't need this either. Oops. Okay, there we go. True, 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 true. That is great news. That's what we want to see. We want to see 4 trues. Then we see sat, we see true. We see unsat, and well, I mean, unsat is unsat. There's nothing to check. Obviously, checking negative 1, 1 is pretty silly. Again, we could filter that out. That was something I had mentioned. This true, and the other is false. Yeah. So now, in this case, actually, we don't want to yield anything. We just want to return. So now it's all trues. Yeah. Now, in this case, we get true, true. I mean, that's good. But we know there's more solutions, I think. Are there more solutions? I thought there were 3 solutions. So now we want to compare this to, like, let's just use a pi sat or something. Let's use or pi I don't really care, anything that's going to give me all the solutions. So now we can actually start, like, getting down to brass tacks with what is going on here. Yeah, that's right. We need to use this one. Okay. So I see 4 solutions and 4 solutions. I see something I like. I see one solution, one solution. I see something I like. I see unsat, unsat. I like it. One solution, one solution. How did it get 4 literals before? Yeah, before that happened. I guess the empty clause case hit. Yeah, there should be a way to avoid this. In other words, I'm okay with seeing 2 in here, but I'm not exactly that okay with seeing negative 3, 1, and 4 in here. Or maybe I should just ignore them because, yeah, they were just potential candidates. Yeah, it's definitely not trying every value. Anyways, we can look at the simple cases, we can figure that out. So, okay, so it is missing one solution here, and that solution is this one, negative 1, negative 3, negative 6, negative 8. Oh, I think I know why. So we're actually getting close to having a working DPLL solution here. Okay, yeah, interesting. Well, it should be okay. We're passing the clauses map. Does the positive and negative clause. I mean, it takes a random variable from the map and it just adds a clause forcing that value. Okay, I almost want to, like, not see this anymore. I kind of want to see it because I want to tighten the code a little bit. In fact, this isn't terribly inefficient. It's, you know, not totally ideal, but I want to know why something feels like it's up here. I see, yeah, I mean, and this is the most telling right here, because 7 minus 7 is definitely not enough. 7 is not enough to simplify this Boolean equation. Because 7 could have 6 or minus 6. It's making an arbitrary choice somewhere. We have to fix it. I mean, there's no choice. This is obviously wrong. And it's cutting out too many solutions. Making some more coffee, and this is happening now. Again, we could do the same method for the DP method. We don't have to like use the case splitting. The case splitting seems like a complicated one to implement. I don't know, something about it isn't. This is much more natural to me, the way we're doing the DPLL. Of course, the DPLL can be done the other way too. There's, as I say, two ways, and we've done one way, one the other way. And again, I think to have the best, deepest, proper understanding of all this, you want to do them both ways. That's really the right answer and the right thing to do. So, because then you understand the different rules that you can apply. Well, where is this? One thing we can ask is, where is it getting 6 or minus 6 from? Actually, it's a good question. I need to do something, but this is going to be the big question is the 6 minus 6. So we got 6, but what forced it? Obviously, it got forced in unit propagation and pure literals, but that should not have been forced. So we kind of want to know where it got forced in here. Huh. So minus 7 I see here. It finds 6 and 8 right off, and minus 8 right off the bat. Something can't be right with that. Oh, so yeah, that's it. Okay, I know the problem. So this is like kind of like a technical problem with how we. Okay, so the reason it's finding 6 and minus 8 is because they are pure literals. But the problem with pure literals is it doesn't mean they have to be true. I mean, it's kind of uh, um, if they're alone in a clause, they do. But this is weird. Because just because minus var never occurs in a clause doesn't mean that var has to be true. And so we're getting this like little uh, situation here where we're going to miss solutions if we want to enumerate them. But in terms of deciding sat or unsat, this is okay. But if we're enumerating, it seems like we don't want to do this. Oh, that was the wrong one. We want to do it over here. Again, this is why I'm saying you almost have to think in two different ways depending on which set of rules you're going to apply. So in this case, we do not want to call pure literal. We want to just, oh, yeah. No, still not working. Oh, look at this. It doesn't include 6 in there at all now. So, because it doesn't, yeah, it's, uh There's cases where it has to be true, but there's cases where it's like just irrelevant. So we don't want to force it to be true. I mean, one idea is just to say what the pure literals are because we know that they, uh, and not to put them. If we forced it as a pure literal, then we don't want to put it in the final equation without putting all of its toggle values as well. That's probably why pure literals should be done after the unit propagation. And then we should probably save which ones we actually forced that way and which ones we didn't. That doesn't really work either, because we would do this too early. I mean, at this point, I kind of agree that this is the solution, but again, we are not enumerating all of them, and I don't like that particularly. Yeah, so how to use DPLL to enumerate all the solutions, kind of in an efficient way, it seems tricky. But I think this is basically right. We can't use the pure literal, but literals that are missing, we can just use iter tools and just go through all combinations. So one thing to check maybe is, do we have them in the map? Yeah, you see, we have it in the map still. Okay, that's a easy way to do this. So, but again, there's kind of like, of course, exponential possibilities, but we want to enumerate them, so we might as well do it. Oh, that's easy then, relatively speaking. I mean, what we can do is we can get all of them. So we know that it's going to have itself and its -1 in there. So we can just use this same idea we do somewhere here. The problem is we'll need to then use I think it's itertools dot. Oh, actually, um, yeah. Well, we're gonna there. We know there's gonna be 2 to the n combinations of these, so uh, yeah. I guess we just set the free literals. So we have our free literals here, and then what we'll do is we'll take our free literals and we'll just kind of use a simple 2 to the n enumeration here. We don't need any iter tools then. We can just negate a few of them and add them to the solved variables. So, you know, for one shifted left length of free literals, so it would be 2, for example, in this case, or it'll go through 0 and 1, yeah. And then what we can do here is we can just add them. I guess we don't even need to necessarily do that. We can just do it like this, I suppose. And we, of course, we have to go through this again here. This is just some tricky little Boolean trick we have to do here, and then we can just say m if one shifted left I and wait, Python else minus m. I guess it's like and x. Does this actually work? Won't even construct a list here. We'll just kind of do this on the fly. Didn't work. Still didn't work. Wait a second. This should probably be +1, I guess. Yeah, it should be +1. Still doesn't work. So the length of this is 1. 1 shifted left 1. Oh no, that's 2. That's actually what we want. Oh, we're returning too early. That's why I got thrown off here. We definitely don't need that +1 there. Okay. And now I can be happy with this as generating all solutions. Yeah, it generates them in a different order, but that's okay. Okay, I mean, actually, this looks okay. feel like I need a bunch of really good test cases to be sure about like kind of nonsense that could creep in where you have like these tautology clauses or other things like that. Again, we can just filter those out up front. Actually, we could filter those out without even building the map. That would be faster, but we will keep it general purpose. So this actually looks pretty much right now. We're getting like the same solutions. Of course, we can always now try the random instances, but I'm guessing they're just still too... we're still too in it. Oh. Wow. So how do we want to validate this? I mean, this is kind of a... For now, I think we'll just print the number of solutions. Okay. Instead of printing solutions, because obviously it's too noisy here, actually it was good for this. Let's actually leave this code be. And let's make like a different set of code for validating with known good SAT solver or something. So we assume that the other SAT solvers have handled all the little edge cases and details. We can actually, well, we ultimately would probably want to just convert these to sets. So yeah, of course we want to make sure that we don't ever get, well, they should all be true. That can be an assertion now. So we can actually totally change this up and just say, yeah, I mean, it depends how much we trust the PySat or whatever, but one thing we can do is just convert these to... Well, a tuple, yeah, and this could be a set. This could be a frozen set. So we can actually just make some kind of like strange assertion here. Well, it's not that strange, but we're going to just say that they're equal. As long as we've done the right things here, it should work. And if something's not working, we can just kind of print, for the time being, something for a reference. Oh, a bunch of them were working. Wow. Or yeah, so some of them are working, and then we get to one where it just didn't work. And it's a mess to try to figure out what happened here. Okay, I might want to print these on separate lines. So, where did it fail? It failed here? So this is like the next point of trying to figure out what's going on. So this found more solutions. How many did this find here? Yeah, one solution, one solution. I mean, a lot of these are the same. It's looking very, very hopeful now. We are indeed solving SAT instances now. The code is feeling a lot more stable. So we're near having a DPLL solution. But again, the fact that it, is able to solve, 8 instances, and then it gets to one that something happens here. Because this is what, 1, 2, 3, 4, 5, 6 solutions, whereas this gave 1, 2, 3 solutions. And the only thing to do is like to try to start matching it up. I see this solution. I see it's the same as this one. So it missed some solutions to this particular SAT equation. 1, 4, 6, 8, 10, 14, 15, 16. So I'm gonna like take this out of here and like put it so we can kind of like look at this. And start just saying, okay, can we see which ones we're missing and which ones aren't missing? It'll be kind of hard to find a good explanation for why this is occurring. Hopefully it's just a simple little bug here, so we can see that like this is our first versus our second one. And where do things go wrong here? Okay, I see. Fortunately, they're in the same order, I think. 15, 16, 17. Yeah, this one is the same as this one. No, it's not. Oh, that's where it went wrong. So 20 and minus 20. Okay. Okay, maybe this is simpler than I think right now. Maybe this is just some thing with the free literals. Because now it's obvious to me that we missed a free literal, and hence why there's half the number of solutions. Oh wait, is it in the tautology? Yeah, all these little details coming into play. Wait, I see. No, that's a different equation. Yeah. I don't see it coming through in the tautology. Okay, I know the problem already. The problem is it could be. Yeah, actually, no. Actually, I don't understand the problem then, do I? Some little issue going on here where something should be becoming a free literal. Okay. There we go. Minus 20. Ah. Yeah, this is kind of misleading though. Because the empty clause is obviously a unsat. Isn't helping. So far that does not really help. Neither does this. I do realize it's deleting it in here. There's some kind of weird contradiction going on here. Because it obviously either it had to become a solved variable, and this is always a copy, so it's okay. Either it had to become a solved variable, or it had to stay in the map. Yeah, I'm realizing this tautology could be a problem because it would eliminate a free variable, so we may want to think about that case, but... Huh. If it becomes a unit literal, it has to be forcing the value of it. But then we're going to return it. Okay, can I print the instance? That might look horrible, but... So here's my instance. Do I see 20 in here at all? Must be in there. Yeah, I see it. I see one occurrence. (20 minus 20 minus 20 minus 20). I mean, I do see several instances of 20 in this formula. This looks impossible. I mean, either it's a solved variable or it has to be a free literal. There's nothing complicated going on in here. Don't see how this could happen. That's so weird. 20 is nowhere to be seen. Again, I'm suspicious of this case, but it shouldn't be the case, actually. The more I've looked at it, I haven't seen that going on, so I feel I shouldn't be that suspicious of it. It doesn't look like that ever happens. Definitely not hitting the tautology code. It's obviously not doing anything in here. We don't call these. The only place it could be deleted from the map is here. The only way that happens is if we add it to the solved variables, which we return. There's no other return here. Oh wait, that's not gonna work, is it? Oh no, it does. Okay. Oh. I'm like really just stumped how this could be possible. I mean, this is just ridiculous. Absolutely ridiculous. We never remove anything here. Except in this area. We're always extending this. This is a copy. There shouldn't be any issues there. It's absolutely defying logic here. Something is up. I'm wondering if some thing like this isn't working. What if I did p dot copy? Would that be better? But I don't see that. It should be a copy. I like the other way better. But obviously doesn't help at all. It's the same issue. Or is it? Yeah. 1, 2, 3, 1, 2, 3, 4, 6, 7. Doesn't matter. This is ridiculous. Only thing I call is unit prop. Something it's absolutely frustrating. It's obviously this is not like something you could possibly expect to happen. It's just too weird. It's just too weird. Just a simple little check. That already happened. Oh yeah, that no, that won't work. That won't work. Yeah, come up with a trick to figure this out. I mean, we could always just focus on that equation and get rid of the previous ones, so we can start writing weird debugging code tricks all over the place. Wait, oh no, no, no. Well, another thing we can always do is we can basically we could check that the free literals and the solved vars, they should be invariant in that at any time the free literals and solved vars should be of length 20. So if we ever have a situation where this isn't true, we know there's an error. And so that's probably we should just say that there should be something like invariant about this. Oh yeah, because we have some other cases in here. I don't really have a good way of knowing at this point what that should be anymore. Obviously, it was 20 was obvious here, but as we've eliminated a lot, it's hard to know that it still needs to be 20, unless we just get rid of this. Start with 20 equations. Okay, there it is. Okay, I mean that's helpful though. That is very helpful. So as I said, okay, that's another really nice trick that you can use when you're debugging is you can look for these types of invariants, and you know that the minute they go wrong, that things are spoiled. Oh, that's weird. Oh, look at this. It's because we've put, yeah. Okay, so I'm gonna, again, this invariant's not gonna hold for the unsat case, where we are seeing unit literals that should be making this unsat. Yeah, it should have made an empty clause, so. Different ways we could solve that. Um, one thing we could do is, just do this thing. Yeah, so okay, that precludes that. And where are we asserting it? On line 121. So it's actually happening up here. Okay. I see we're forcing one of two values. Actually, they're free variables here, aren't they? Uh-huh. Oh, interesting. Minus 15, 15, 17, minus 17. Seventeen and 2. I mean, I'm counting 17 and 2 very cleanly here. So where did 20 go? I must be doing something really stupid here. So weird. I don't know. 3. Uh-huh. So what happened to the map? Okay, so that actually this is now we're really narrowing this down right here. That's good. Um, so we want to look at a map versus this new one that we're building. That's where things are going wrong. Okay. 3. Aha, minus 20, empty, 20, empty. Okay. Oh. Oh. Okay. After all that, it's like one of these obvious things, and I'm like, okay, don't need any of this. Don't need any of this. It's a free literal already, but we don't actually keep track of the free literals. So, I mean, the easy thing to do is just to look at the free literals and just add them back to the map, I think. All right, I'm fixing it. End of story on this one. Yeah, that was surprisingly, this is more tricky than I thought this code was going to be. I mean, actually, I thought this was going to be more straightforward. Whoa. Yeah. All right. Anyways, that like fixed that bug, and then we run into the next one and the next one. I actually don't know this is a bug. Could just be a really hard SAT equation. So it's passed about 15 instances. At this point, it's almost like you just leave it be for a little while and just see if it's found a really hard instance. Again, 2 to the power of 20. Honestly, starting to seem quite good, though. It's starting to seem like we have something we can call a SAT solver. It's not that slow either. It's slow without being egregiously slow. But I'm mostly worried, are there more bugs? If there's more bugs, then wait, something's wrong. Something's wrong because I'm looking at my CPU usage and I don't. Actually, I don't see the command prompt. What the heck? This is so strange. Something is up here. Oh, it is using 8% CPU. I don't know, it wasn't sorting before, and I do see the memory going up and up and up and up and up. Perhaps we've found an instance that has too many solutions. Although it's strange that my invariant didn't hold. Perhaps there was a tautology? No. Okay. Put this code back. I'm reasonably satisfied that we've solved DPLL, but I do admit this is kind of a something where I may want to like do something a little different here. And I'm also questioning how it could be having another invariant failure. That seems strangely suspicious. So one thing we could do here, just to get some idea, is to see what this one thinks. Yeah, 55 solutions. So it is another bug. It is another bug. Mm-hmm. Probably we're getting close to the last bug, at least in the test cases I have, because I don't know. Yeah, I don't know what's going on here. Comment this back out. And oh, it's not making it very far. Oh yeah, we said we need the other statement. We can't just put this invariant here and try to catch something. So 12 and 9. So, oh, it got a double. It got a double solution. Oh, that could happen, couldn't it? Yeah, actually, I said a long time ago we shouldn't do it like this. We should do it like that. Ooh. Are we doing better, though? $13 and 8. So I see 17 in there twice again. Which technically should be impossible now. So, 17 in there twice. This is so strange. Yeah, keep hitting these weird situations where obviously something silly wrong here, and I don't know exactly what it is. Okay, maybe. Maybe we should print S here too. So if we print S, we see, okay, -8 and 17. So kind of a good question how it's able to do that. So I just want to see, is 17 still in the map? Okay, I'm just going to take a look at this. Wow. Definitely 17's not still in the map. So how is it getting back into the map? Doesn't make sense. We copy it here. Just add lots of debugging. See if we can figure anything out here. Quickly, hopefully. I see 17 came back. I do see 17 has just, yeah, it is a unit literal, and -17 nothing, so it's okay. I see here too, yeah. And it took it out. So how is it getting back in to the map? This is totally beyond me. I feel there must be like a little bug here. Can't see it though. can't see it. Again, we can also just write another simple yeah, I mean, it's hitting this exact case where uh, maybe I should put it here. Oh, no, didn't hit that. I mean, I see we could choose a free literal. In fact, we shouldn't do that. Of course, a free literal should never be chosen as the it should really be the next one that's not a free literal. That's true. We want to divide these up into free literals. In fact, free literals we could just record and just start deleting them altogether because we don't really care about them at all. We're going to deal with those way later where they have to just contribute to a 2 to the power of something extra solutions. Uh, yeah, I guess we need integrity checking codes. Something's up here. Okay, -8, no problem. That is map. So actually, we don't know what z is in this case. It's 17. Yeah, wow, we do know. Actually, we should have known. Oh, that's even worse. Is it in a clause? Okay, I think I know. Something is up where 17 is not supposed to be in any clauses. I have a feeling I know already what's going on. Probably that whole preclusion case where we say if X is not in the map, but oh, I see. It is. There is a 17 still here. So somehow 17 became a solved variable, yet we still have a frozen set with 17 here. But it was deleted from the map? Okay. I think I know why this is happening. I'm going to fix this. One moment. Okay, so I know how to fix this. What's happening is that these cases where you can have a 17 and minus 17 occur in single clauses in the same iteration. Basically, that is our unsat case. That's the only time I think, yeah, that you could get an empty clause. I mean, unless you were given an empty clause at the start, it might still be better to just, turn these into an empty clause. But there's a special case here where you have two clauses of length 1, and one of them is the positive and one is the negative case. And it's the reason we're hitting this case here. And actually, it's the reason this whole thing isn't working. So somehow, we're going to want to check before we even do a unit propagation that we don't even, well, I wouldn't say we don't do anything, but we want to handle that case basically specially. It's an unsat, and we can. Yeah, it's got to be an unsat case here. Oh, I think, yeah. Basically, the problem is we've added a clause back here when we actually shouldn't have done that. So it must have like 17 and negative 17. Yeah. So it must. It's weird though. I don't see the negative 17 here at all. Is there a. Hmm. I almost want to look at the clauses before this is happening. And then I can kind of. Oh, wait. Okay. So I don't see why it wouldn't have just eliminated 17. It's a lone clause. Well, now I know the work involved in getting this done. It's more tricky than I thought. I see 17 returned, and I still see 17 here. How on earth is that happening? Doesn't make any sense. Yeah, that's the problem. Minus 17 shouldn't be anywhere, so it doesn't make sense. This is all it should be doing here. Clauses.remove C. Is the map screwed up? I have to kind of just keep tracing these little things here. There obviously some little tiny thing is wrong here. It's annoying because it feels like it's almost working and it's just tied up on some little detail. So I guess 17 was deleted from the map because we don't see it there, but it didn't get deleted here. So yeah, oh, I see. Oh, that's the problem. There is definitely a corruption going on here. At the moment, I don't really know where it's happening. Uh, After all this work, it's like obviously I see that there's a 17 in there, but there's also um, not consistency with the map. So maybe a stronger assertion here, because it seems like this code with the free literals is causing the problem, but again, it seems then that the map hasn't been managed properly. Somewhere there's an inconsistency. Obviously, somewhere seems to be in the unit splitting. Um, I just want to kind of double check some cases that I'm sure shouldn't happen because these are tautologies. And of course, they're not happening. So where is the inconsistency here? Well, one thing to do is just to write the code to check the map as got all the clauses. Or, you know, basically you can say for C in clauses, or X in C, assert map sub X, assert C in map sub X. Yeah, 17. There, that's exactly the problem right here. Happens right here. Oh, this isn't right. I'm doing this wrong. Obviously, that is a reference. Uh-oh. I mean, I'm totally at a loss here. Absolutely seems nonsensical to me. What? All right, this is totally screwed up right here. Whew, I think I have broken Python. Is all I can say. I can't. You know what I mean? This doesn't make any sense. Now it works perfectly. It solves every single one. And all I needed was this. This is really no wonder this is absurd. This is totally absurd. Useless for loops are causing it to work. Oh, I guess I fixed it before somehow. I don't remember how I did it, but yeah, okay, so it works. Okay, well, that was really weird. I don't know. That was really, really weird. Okay, it works. That's it. Solved. We have a SAT solver. Okay. And it uses only one rule, the unit propagation. That's why they say that one is the most expensive. Some of this free literal stuff feels a little hacky to me. Um, yeah, I don't know. I don't know. It works perfectly, is all I can say. We can solve SAT formulas without a problem. And those are actually reasonably large instances, so I mean, well, actually, they're about the smallest for, real hard testing of stat solvers. But, I mean, is a good first place to start. That's not bad. Now, of course, we should use all of this stuff, the pure literals, case splitting, tautologies. We should really kind of move to that level. Of course, as I say, we basically have solved this, and it should work now in a pretty general sense. Um, yeah, I'm actually reasonably satisfied with this now. But again, uh, there's also the idea of using the splitting and the other stuff, because the idea of the splitting rule is that you can eliminate a variable, but still apply something that preserves the sat unsat property. But then, as I point out, you've created like an unknown variable. So if you want to fill in the answer, it creates a problem. Now, what we've done with DP, we could actually do DP. Uh, I'm trying to think if there's again, I want to be careful here because the question is, uh, have I done this really properly or not? If we want to enumerate formulas too, there might be better ways of doing this? Again, that's where this free variable stuff comes into place in the literals. I don't know. The problem with what I'm getting on the internet is there's so many descriptions of these algorithms. So um, I'm looking at the Wikipedia page now just to kind of decide. I mean, the other option you could do is you could keep the unit clauses and not take them out of the formula, and just you not bother with the solved variables. Like there's a bunch of different ideas for what you could do. That actually could be kind of efficient as well, but you would keep finding them. So that's, of course, we could make like another data structure to keep track of the number of well, that maps number of literals in a clause to clauses, and then we'd have to subtract one or move it around. Yeah, everything has a cost, although that actually might be rather efficient. Um, and yeah, the branching literal that we choose randomly, there's definitely considered much better heuristics for that. But again, I don't care about that. It's easy to, again, it's usually based off different counts and other stuff, and there's a lot of theory behind probabilistically what might be the best one to do. Oh, I see. The pure variables are just deleted. Yeah, is what it's saying. Okay, pure literal elimination, as opposed to applying them. Well, it doesn't matter. Actually, they should be eliminated. So why don't we do that? Uh, what am I thinking with that one? It's nice to see it working, though. Finally, nice to see it working on a large amount of instances. Yeah, these are like what we're calling the free literals. So basically, any clause containing one of these types of literals can just be deleted, actually. And I'm suspicious of this code. This obviously isn't a solved variable, which is it's ridiculous. In fact, this seems really suspicious. I think I was looking at too many references. Some of them are just garbage. Because in my opinion, we can do this, but what we do here is we just say for clause in map sub var of negative var. So the one that it doesn't matter because it never has a negative value. I mean, it would matter for enumerating solutions, but that's it. It doesn't matter. Oh, actually, no, this isn't true. Sometimes these have to be true. That's the problem. Sometimes they don't matter, and sometimes they're forced true. I'm thinking how we can optimize some of these things. I, I don't know. Pure literal elimination is, again, you still have to keep track of them somehow. I mean, it's not so simple. Because sometimes the value is forced to be true. Sometimes something else in a clause with it is true, so it can be false. If we want to enumerate the solutions in a different way, again, these are all complicated questions, because if we want to enumerate the solution by banning previous solutions, then we should eliminate pure literals, and we should just say that, okay, um, well, we should ban, or we should get rid of all the clauses with pure literals, because they absolutely do nothing for you. And just assume the pure literal is true. Basically, that's all we're doing. Is actually we are doing this code, so effectively that's all you're saying. But the problem is, if you do this, you can no longer do a search for solutions. So the minute you do that, you get rid of that literal by making it true, and you make the search simpler. But good luck enumerating solutions, because what about when it's false? Then you should also be considering that case and actually just deleting it from the different clauses. So basically, you have to divide the search up into two cases for enumeration. But if you're only concerned with sat or unsat, there's definitely something different in all these different logic of doing sat unsat purely, or doing like some kind of search for enumerating equations. And it's like, I want to do the enumeration mostly. I don't really want to just say sat or unsat. Granted, the sat problem is sat or unsat. If you're really like looking at the NP complete theory, usually it's sufficient to just say the determining sat or unsat is enough. But practically speaking, it's almost useless to say sat without giving a solution and without being able to get the next solution, etc. So this is like something that requires some serious consideration. All right. Okay. I think I'm going to close this off for now so I can, do other things I need to do, but I'm going to come back to this. This is, it's been interesting, needless to say. So, I don't know. Almost want to keep going, but it's, this is a long type of a task to keep up with and make sure everything is properly working. I think almost the DP algorithm might be the next thing to take a look at. That one does seem pretty important to try. That one does seem pretty important to try. That one seems like the next step. Because again, I kind of said I was going to do it, and then I kind of skipped it, and maybe it was just bugs that was plaguing it. It's kind of a good question. Again, I have some tricks that I've been coming up with to try to figure out how we can do something more with this. In fact, does this work? Have we even tried it? Oh, we didn't even put this code. Actually, maybe we should keep going. I'm trying to think if I need to have dinner or something like this, or if I should just keep going. Oh, ouch. Okay, so this is giving me 4 answers. This one's printing some stuff out. It says sat and it just returns. Oh yeah, there's too many solutions. This one, I shouldn't do that one. Honestly, this looks better as far as I can see. I mean, I see it's giving sat or unsat, and these are true cases. This doesn't. Yeah, this is right actually. This one would be right if it enumerated, which it doesn't know how to do. I think we'll have to do like some kind of banning solution method. Trying to remember how to do. Oh, actually, I have that already, don't I? It's right here because I have it for the Pi crypto sat. I can't even find it. Pi crypto sat, yeah, has this. So what it does is it adds, yeah, minus x for everything in the solution. So it just negates the whole solution and says, okay, and this or this or this, not, well, basically not this or not this or not this or not this. So one of the things has to change. It's a great method for the DP algorithms. So I think we're going to do just that. So what we'll do is we'll define like a DP all. And yeah, we'll do exactly this type of thing. So solution equals something. And then we can just say, yeah, you have to ban each solution one by one. But this works perfectly legitimately. So you can just say clauses, append. It's not efficient by any means, but this. So this is going to return a single solution. It's not going to yield anything, is going to be the decision here. It's going to return like sat or unsat. Oops. Which is either going to be empty or not empty. Or none, I guess. Yeah, so, okay, at least we have like a sat unsat idea here. Okay, this doesn't look good. Oh yeah, we know. Well, we know we're not getting solutions here. So actually, it doesn't really work until we start to get more headway on this task. Pure literal should actually be okay. Again, with this type of enumeration, this should be absolutely fine to do. So I'd like to look at the map to see if we're going to have like a free variables. Basically, we just have to adapt this. This case, it'll be a perfect one to adapt. No, so far I don't see anything in there. Ooh. Oh, it's changing the formula. That's a problem. Okay, well, we should just copy it in DPL. We'll just assume that you're not allowed to touch the original formula. Okay. Doesn't look good. Yeah, -1 is just not enough. The problem with this, and this is the tricky part, is it feels like I have to do the DPLL anyways for, after I've figured out it's SAT. But also this unsat isn't properly working, as I can see, so... Again, this isn't too bad. It looks kind of hopeful here. But I don't know, this is definitely getting an empty clause when it shouldn't be. All right, well, these cases need to be studied in detail to get anywhere with this. And then we'll see if this exponential space complexity this should somehow simplify, though, in some way. I'm kind of wondering why combinations are far worse. It's very interesting. Because this should somehow be, a lot more memory intensive, but I'm thinking it should be reasonably competitive with this one. But at the end of the day, we do have a working DPLL solver finally. Not the most efficient thing in the world, but it's a pretty good start at trying to do this. And it does use generators. There's a lot of good things about this. Yeah, we should use generators other places. As we increase the size and everything, we're gonna, improve the performance and figure out how to, well, we'll write better testing code. For now, yeah, most of this doesn't look too bad. This doesn't look too bad anymore. I don't like that it's, got a little bit of ambiguity with like cases like this. But as I'm seeing it, this shouldn't really be an issue. Yeah, I can kind of get rid of a lot of this test code. Yeah, this we know isn't true. That's actually unsat, so. But although actually we could, short circuit. So, okay, unsat comment. This next clause's idea, I mean, okay, whatever. Basically, I'm reasonably happy with the code now. But I feel there are some cases I haven't thought about, maybe in the case splitting. Basically, we're going to have to go through this in micro detail until it works. Yeah. So all I see is, yeah, this -231. This one works, actually. -1, yeah, it works. This case, actually, the first test case is, oh no, the first one's this one, yeah, where there's 4 solutions. That one doesn't work. By applying the splitting rule, we just figure out that it's sat, but we don't end up with a solution. Because we eliminate 1, and then we find that, oh, okay, 2 and 3 have to be, possible to satisfy. Everything just simplifies, but it doesn't tell us if it should be 1 or not 1. We've kind of, applied this rule that makes it totally ambiguous as to whether it should be one or the other. Actually, I think I'm wrong about that. I think this can start giving us a solution. In other words, this almost is a point where you're saying that if it turns out sat, you know that there's solutions on both sides. I have to think about that. Okay, well, I'm going to continue this later. This has been interesting, though. Definitely getting somewhere with this and realizing there is a certain amount of trickiness with getting this right, but it isn't too bad. Again, we don't do any fancy tricks, so we're able to use some sets and simple data structures, but trees and other kind of data structures are better if we're going to do some more fancy type of tricks on this. So, okay, thanks for watching, and we're going to close this off now.